All right. Good morning, everybody, especially to Michael, John, Christian, Prince, and Trisha. Siguro ito yung mga mainstays all throughout the Math 155 lecture sessions. Ano? So, no look na, tatlong linggo na lang tapos na ang semestre. It's as if parang kahapon lamang tayo nag-uusap about the completeness axiom. And now we are ready to conclude our discussion about, or the first part of advanced calculus. If you got really excited or interested with advanced calculus, baka naman gusto nyong i-take yung Math 156 as your elective. Ano? So kindly think about it. It will be a continuation of the things that we were talking about here in Math 155. So I think kino-cover nila yung function of several variables. So that would be a nice thing to learn if you're really into real analysis na. But for our class, I already uploaded problem set number 3 nung Monday kahapon. You can try to answer it even though the deadline is on June 9th or last day of classes. But I encourage you to submit as early as you can. Submission bins will be available probably by the end of the day today. So para masimulan nyo nang makapag-submit at masimulan ko na rin makapag-check. All right? Now, may mga utang pa ako sa inyo. I started grading homework number 6. So siguro nakasampu na ako na na-checkan kahapon. And I'll try to finish grading problem set number 2 within the week para medyo nakikita nyo na ano yung itsura o ano yung probable shape ng inyong final grade. We have a final exam that will be due per the schedule set by the registrar. So pakiantabayanan natin yon. But as I mentioned earlier, the final exam will be a reflection paper. I'll give you the guide questions towards the end of the semester, so probably next week or week after next at the latest. So yun yung mga natitira. And then we have a couple more sections in the class. Pero that reminded me, I'll give you still a couple of homeworks 7 and 8. Siguro isa next week, isa due next week, at saka yung isa naman ay due sa last week of class. So, them. But I think we can finish the discussion about the course this week, all right? So matitira na lang mag-homework na lang kayo next week at saka week after next if we can really finish the discussions within the week, okay? Now, let's go back to our discussions. I think last time we finished with the Lebesgue's criterion for Riemann integrability. Tapos sinagot ni Lebesgue yung tanong natin na gaano ka-discontinuous ang isang function para or hanggang gaano natin kayang i-push yung pagiging discontinuous ng isang function while requiring it to be Riemann integrable. Kasi nalaman natin from previous theorem that if you have a countable number of points of discontinuity, then your function will still be integrable. Okay? Kaya lang sabi natin, gaano ko kayang i-push yung pagiging discontinuous niya, tapos nare-retain natin yung pagiging Riemann integrable ng isang function. And the answer was given to us by Lebesgue, and Lebesgue said na, okay, kapag ang function mo ay ang isang function ay Riemann integrable if and only if the set of points at which it is not continuous has measure 0. Okay? So ito yung parang characterization natin para sa mga Riemann integrable functions. So basically, f is Riemann integrable if and only if it is continuous almost everywhere. Yun yung term natin na almost everywhere. Ang isang property ay nag-hold almost everywhere if and only if yung mga points kung saan siya hindi nag-hold ay may measure 0. Okay, tapos nakakita tayo last time ng mga sets na measure ay 0, like the finite sets. So yung finite sets, kasama doon yung empty set kasi 0 yung number of elements ng empty set. And then also countable sets are also of measure 0, even if they can be infinite. Even if they can be infinite. Okay, so measure 0 pa rin sila. So we have a lot of things or a lot of criteria for Riemann integrability. Now, the question now is, paano tayo makakapag-compute ng Riemann integral? So, yun yung kulang. Ang dami nating pan-check kung kailan siya ay Riemann integrable or hindi. Tapos alam natin ang definition ng Riemann integrability ay kung nag-exist yung Riemann integral, and the Riemann integral is the common value of the infimum of the upper sums and the supremum of the lower sums. But again, we noted that that process is very tedious. Okay? So ngayon, titingin tayo ng iba't ibang paraan. Actually, I forgot if it's just one or two methods kung paano makakapag-compute ng Riemann integral knowing that the function we are dealing with is Riemann integrable. And the first result that we have for this is the Archimedes Riemann Theorem. Okay? So ang assumption ngayon, ng mga theorems nating titingnan, ay dapat integrable muna. Kasi there's no point of talking about what the value of the Riemann integral is if the function f is not Riemann integrable. Okay? Now, Theorem 5.5 is sort of a combo. It is a combo between a test for Riemann integrability. That's what the first section or the first statement in the theorem is about. And the second is how to compute for the Riemann integral if we know that f is Riemann integrable already. Okay? So tingnan natin yung unang condition. Sabi sa theorem, f is integrable on the closed interval AB if and only if there exists a sequence of partition inducers P sub n such that the limit of the difference, or actually it is the limit of the sequence formed by the difference between the upper Riemann sums and the lower Riemann sums relative to each of the partition inducers in the sequence as n approaches infinity is equal to 0. Okay? So dapat daw, para siya ay maging Riemann integrable, makahanap tayo ng isang sequence ng mga partition inducers, P1, P2, P3, P4, P5, and so on, such that the limit of the sequence formed by the upper Riemann sum minus lower Riemann sum of f with respect to the partition inducer P sub n, okay, approaches 0 or converges to 0. Okay? So pwede nating tingnan ito yung xn natin. Yan yung terms dun sa ating sequence. Kapag yung sequence ng mga differences na yan ay nag-converge kay 0, then the function f is Riemann integrable and vice versa. Okay? Now, if that is true, then the Riemann integral is either the limit of Riemann sums or the limit of the lower Riemann sums. So yun yung sinasabi ng Archimedes Riemann Theorem, which, if you think about it, is not a big leap from the previous criteria that we had, because we said last time dun sa isa nating theorem, I just forgot the number, and sabi natin ang isang function f ay Riemann integrable if and only if for every epsilon greater than 0, there exists a partition inducer P such that the upper Riemann sum of f relative to P minus the lower Riemann sum of f relative to P is less than epsilon. All right? Yan yung characterization theorem natin. I think it's theorem 5.1, the Riemann, the integrability criterion. Okay? Pero kung isipin nyo, translation lang ito, di ba? Nitong sequence, itong limit statement na ito. And basically, that's what we're gonna see in the proof of theorem 5.5. Tingnan natin ang proof niya. Siyang hatiin sa dalawang state. We're not supposed this limit statement is true. Okay? So tapos sabi ko, kamukha to ng integrability criterion theorem 5.1. So dahil si f, ang assumption natin dito ay si f ay integrable, gusto ipakita na yung limit ay equal kay 0, gagamitin ko yung integrability criterion. Okay? In particular, I'm going to use it for epsilons of the form 1 over n. Sabi ng integrability criterion, f is Riemann integrable if and only for all epsilon greater than 0, you can find a partition inducer P such that this epsilon statement is true. Now, purbahan ko yan. Totoo raw yan sa lahat ng epsilon. So, pipiliin ko yung mga epsilon to be of the form 1 over n. Okay? So, ibig sabihin, for each of the 1 over n's, there will exist a partition inducer, P sub n, such that upper minus lower Riemann sum ay less than the epsilon value that we had, which is 1 over n. Kaya lang ngayon, pwede nating kunin yung limit ng lahat ng sides ng inequality. Oh, by the way, this guy is always greater than or equal to 0 because we know that any upper Riemann sum is greater than or equal to any lower Riemann sum. Kaya meron tayo dyang 0. Tapos kukunin ko yung limit ng lahat ng sides ng inequality, right? So that means the limit of this guy is 0, limit of this guy is also 0, and then by the squeeze theorem, yung limit ng nasa gitna must be equal to the limit nung nandun sa magkabilang dulo. All right? So that means the limit of f of pn minus L of fpn is equal to 0. The common limit dun sa magkabilang sides. Okay? So essentially, what we have found is a sequence of partition inducers mga p sub n such that the limit of the upper minus the lower Riemann sums is equal to 0. And hence the first statement is proven. And you see the main ingredient in this proof is nothing more but the integrability criterion plus the squeeze theorem. Ano? So talagang naging translation lamang ito ng integrability criterion. Okay? Now let's look at the second, the proof of the second statement or the converse. Sa converse naman, i-assume natin na merong sequence of partitions such that the sequence of the differences of the upper and the lower Riemann sums converges to 0. Okay? Gusto nating ipakita ngayon na si f ay Riemann integrable. Now, paano natin to gagawin? Well, I'll capitalize. Mukhang nawala pala yung screen share ko. Nag-hang din ba siya sa inyo? Hold on. Ulitin ko, guys. But while I'm restarting my screen share, any questions with the first proof? All right, thank you, Michael. Okay, so doon naman sa second part, i-assume natin na merong sequence ng mga partition na yung difference between the upper and the lower sum ay equal kay 0. Gusto ko ipakita ngayon si f ay integrable. Ano? So pwede kong gamitin ulit si integrability criterion kasi siya ay if and only if din. So kailangan ko makakita ng partition such that this guy is true para maging Riemann integrable siya. Well, ito yung alam ko. So pwede kong i-apply dyan yung definition ng limit ng sequence kasi ito ay isang sequence, right? So by the definition of the limit of a sequence, we know that for any given epsilon greater than 0, meron tayong starting index capital N na mahanap such that after that index, yung upper minus lower Riemann sum ay magiging less than epsilon. In particular, totoo ito kapag kasi n ay equal kay capital N. So for any given epsilon, nakakakita tayo ng isang partition inducer, in particular P sub n, such that this epsilon inequality is true. But this is exactly the epsilon inequality we're looking for to use the integrability criterion. So therefore, by Theorem 5.1, ito ay magko-conclude na si f integrable sa closed interval AB. Okay? So that ends the proof. Okay? So, ganun lang kasimple. Sana ganito na lang yung mga nasa problem set, ano? So, napaka-natural nung proof. And that is to be expected because as I've mentioned, pagbasa ko pa lang ng Theorem 5.5, inisip ko na kagad na ito ay parang restatement lang integrability criterion in terms of limits. Kasi yung integrability criterion natin, iniwasan yung paggamit ng limits. Pero Theorem 5.5 reveals that actually this is equivalent to Theorem 5.1, the integrability criterion. Ito nga lang naka-phrase into a more or in a more operationalizable manner kasi limit ito, mas practical kasi kaya natin mag-compute ng limits ng mga sequences. Okay? Now, there's one more thing to be established here. Gusto nating ipakita na totoo itong equality na to because this tells us na kapag si f ay Riemann integrable, then to find the value of the Riemann integral, it suffices to find the limit of the upper Riemann sums and the lower Riemann sums as well. Okay? So, ganun yung gagawin natin dito. Right. So, tingnan natin kung paano sinulat proofification. Kasi medyo merong mga pwedeng shortcut, ano? So, may mga sobra ditong inequality. So, umpisa natin yung analysis by at the lower Riemann sum of f relative to the partition inducer P sub n. Okay. And then I know that this guy is less than or equal to, actually, buburahin ko na to. I hope you don't mind. Okay. Buburahin ko na rin yan. Si lower Riemann sum of f relative to P sub n, siya is strictly less than sa sarili niya plus some epsilon greater. Oops. So here, okay. So, yun yung condition. Pwede na natin kalimutan ito kasi nag-add lang naman ako ng epsilon. Alam ko greater than yan. Okay? And then I know that the lower Riemann integral is the supremum of all the lower sums. So that means this guy is less than or equal to this guy. Alright? Kasi nga, supremum ito ng mga L. So, ibig sabihin, kahit anong L ay mas maliit dun sa supremum. Tapos, I copied over the plus epsilon. So, we have a less than or equal to dito. Tapos, what do we know about f? F is assumed to be Riemann integrable. Remember, dun sa part 2 ng statement, si f ay Riemann integrable ay part na ng assumptions. So, dahil si f ay Riemann integrable, the lower Riemann integral is equal to the Riemann integral. And so, we have the equality over here. So, what we have shown here is that the lower Riemann integral is strictly less than the Riemann integral plus epsilon. So in other words, if we will subtract from both sides the Riemann integral, so we'll get the lower Riemann integral minus the upper Riemann the lower Riemann sum minus the Riemann integral has absolute value that is less than epsilon. All right? Kasi nga, actually, ito, ililipat ko sa kabila, L minus Riemann integral, that will be less than epsilon. Okay? Tapos, I can do the same thing, pero mag-start naman ako sa upper Riemann integral. Ito ay mapapalitan ng upper Riemann sum. Ito ay mapapalitan ng upper Riemann sum. Tapos ito, instead na lower, consider ko ay upper. Tama ba? Infimum to no? Or baligtad. Yung baligtad naman yung makukuha ko. Kasi ito, working backwards, ito ay equal dito sa upper Riemann integral. Tapos ito ay greater than or equal to sa upper Riemann sum. Tapos ito ay greater than, or pwede ako mag-minus epsilon. Paano ko ito mapapalabas? Hold on. Sige nga, isulat ko na nga. So yung upper, pabaligtad siguro. Yung Riemann integral of f plus epsilon ay magiging mas ay equal sa upper Riemann integral plus epsilon. Tapos this guy will be what? This guy will be smaller than an upper Riemann sum plus epsilon. Kasi ito ay infimum, greatest lower bound. So I will get this guy. Kailangan ko yata minus. Okay, gawin ko tong minus. Gawin ko tong minus. Tapos ito ay magiging minus. Tapos this guy would be less than the upper Riemann integral integral of f with respect to the partition P. Okay? Tapos, I can play with this inequality. So ito ay magiging integral of f minus the upper Riemann sum less than epsilon. So ibig sabihin yung absolute value ng upper Riemann sum minus the Riemann integral will be less than epsilon. Okay? So, and then remember here, the choice of epsilon was arbitrary. Epsilon is any number greater than 0. Pag kinuha natin yung limit ng pag kinuha ko yung limit nito, makukuha ko ang limit ng lower Riemann sum ay equals sa indefinite integral because this is just a constant. Tapos ito ay limit ng u minus limit nito ay equal kay 0 because epsilon is any number that is greater than 0. So that means the limit of the upper Riemann integral of the upper Riemann sum is also equal to the Riemann integral. And therefore, this limiting statement now holds. Okay? So ito yung isang paraan paano magko-compute ng Riemann integral. Pero ang problema rito ay dapat yung sequence natin ng partition inducers Pn, dapat sinasatisfy niya na ito. Okay? So if you want to capitalize on the second statement of Theorem 5.5, kailangan mahanap mo muna yung partition inducer or yung sequence ng mga partition inducers such that this is true. Pag nahanap mo na sino yung partition inducer na yon, kunin mo lang yung either limit ng upper sums o limit ng lower sums, yon ay magiging equal dun sa Riemann integral. But that is probably not very easy to do at this point. So kailangan pa nating humanap ng iba't ibang mga theorems, okay, for this to really happen. Or at least some ideas on how to construct the sequence of partition inducers P sub n. Okay. Now, the partition inducer na ginamit dun sa Theorem 5.5 ay tinatawag ding Archimedes sequence of partitions or ASP. So to capitalize dun sa limiting process na nakita natin sa pagko-compute ng pagko-compute ng Riemann integral, kailangan makahanap muna tayo ng Archimedes sequence of partition o yung ASP na tinatawag, which is difficult to come by, especially if you don't have any idea where to start. Okay? Now, to give us an idea where to start, tingnan natin yung konsepto ng regular partition. Okay? Yun yung nasa definition 5.6. Now, here, ang isang regular partition or isang regular partition inducer ay isang partition inducer na equally spaced yung mga partition points. So that means that the difference between two consecutive exabytes is equal to a common value. Ang common value na yon ay b minus a all over n. Okay? Kaya siya tinawag na regular partition kasi regular yung value ng pagitan sa dalawang magkaibang partition points. Okay, so two consecutive partition points will have a uniform step size equal to delta exabyte. Right? Now, let's see some examples over here. Let's consider, actually nakita na natin to last time, na-prove na natin ng function f, which is x squared, ay integrable over the interval 0, 1, but we didn't mention what the value of the definite integral is, all right, or the Riemann integral is. Now, to calculate it, i-consider ko yung isang regular partition ng 0, 1. So I will partition it into an arbitrary number of, say, n partition points. Tapos gusto ko maging regular siyang partition. So I am deciding na yung common difference o yung common step size between two consecutive partition points ay 1 over n. So ang itsura ng partition inducer natin ay 0, 1 over n, 2 over n, 3 over n, 4 over n, hanggang makarating ako kay 1. And notice that the difference between two consecutive partition points ay equal kay 1 over n. So this is a regular partition inducer. Okay? Tapos compute natin yung upper minus lower Riemann sum. Okay? So yung upper minus lower Riemann sum, alam natin yan. maximum value minus minimum value, okay, over the subintervals times delta exabyte. But we know delta exabyte is uniform. It's 1 over n. Tapos yung mi minus xi saan nga to equal? Maximum value nangyayari sa kanang endpoint. So this would be what? This would be I squared over n squared minus yung minimum value naman nangyayari dun sa pinaka nasa kaliwa, right? The leftmost point on each of the ith subintervals. So this is going to be oops, nawala. Sulat ko na nga. So this would be summation ng I squared over n squared kasi yun yung function value, right? So sa interval I minus 1 over n hanggang I over n, ang maximum ni x squared nangyayari sa function value nung nasa kanan. Tapos yung smallest function value, which is our little m sub I, siya yung nangyayari sa pinakakaliwa. So this would be minus I minus 1 squared over n squared times delta x sub I. But delta x sub I is just 1 over n. Yan yung common step size. Tapos itong numerator ay I squared minus minus 2I plus 1. Tama ba? I minus 1 squared. Sorry, I squared minus 2I plus 1. Okay. All over n squared. Tapos simplify lang natin. Anong matitira? So ito ay may matitirang summation ng 2i minus 1 over n squared times 1 over n squared. Sorry. Times over n. Tapos look for the formula of summation of 2i. Tama ba yung ano? Tama ba yung algebra ko? Sana tama yung algebra ko. Kaya lang tinatamad na ako mag-expand. Just remember that the sum of I equals n times n plus 1 all over 2, right? So paki-simplify na lang. Ayoko na siyang i-simplify. So magsisimplify daw yan sa 1 over n. To kindly verify that. And 1 over n will approach to 0, right? So limit ng upper minus lower Riemann sum with respect to the sequence of regular partitions induced by 1 over n ay equal kay 0. So by the Archimedes Riemann Theorem, f will be Riemann integrable. So nag-hold siya. So tapos sinasabi nung second statement ng Archimedes Riemann Theorem na ang kapag si f ay Riemann integrable, sure tayo na yung Riemann integral ay equal dun sa limit ng upper sum ng Archimedean sequence of partitions. We have shown that this sequence of partitions, yung generated by the partition inducer P sub n, ay isang Archimedean sequence of partitions. So therefore, kailangan ko lang kunin yung limit ng upper Riemann sums relative to the PNs or the limit of the lower Riemann sums relative to the PNs para makuha yung Riemann integral na x squared. Okay. So ginawa siya dito gamit yung upper Riemann sum. Sinimplify yung upper Riemann sum. Equal siya dito. And the limit of this guy is 1/3. Okay. So in-expand lang ito using yung expansion formula para sa summation ni I squared. Naging ganito na siya. Then this is n cubed. Meron tong leading coefficient na what? Napaisip ako bigla. Tama ba to? Wait, x cubed over 3 evaluated from 0 to 1. Dinaya yung computation eh, no? So that's gonna be 1/3 minus 0. So 1/3 nga yung integral. Pero tama ba tong expansion na to? Kasi kapag kinuha ko yung limit nito as n approaches infinity, magkakaroon ako ng magiging 2. Wait, paano naging 1/3? Or what? Am I overthinking it? Paano naging 1/3 yung limit niyan? Pag in-expand ko kasi to, magkakaroon siya ng 2n cubed over n cubed. Two, three. Meron ditong kulang. I think there should be a 6 here somewhere. Wait, 2/3. Teka, search ko na nga yung summation ng I-squared. Tandaan nyo pa. Sum of I-squared. Yeah, tama yung suspicion ko. Dapat ito ay times 60. Yeah, there we go. So n times 10 plus 1. Okay, and now it makes more sense. Oh, thank you, Michael. Kulang nga siya ng 6 sa denominator. Bigla tuloy yung kinabahan. Kala ko epekto lang to ng kagigising lang. Pero yeah, may 6 nga na kulang, right? So that's why the numerator will have a coefficient 2n cubed. Yung ilalim may leading coefficient 6n cubed. So ang limit niya lang ay 1/3. Okay, then there we go. That would be the integral of x squared over the interval 0 to 1. Okay? Yan, at least naituwid natin, na-correct natin yan, nahanap natin yung correction na yun. Okay, so any questions dito? Because the next thing is we will introduce what we call the Riemann sum, which is just a generalization ng upper at saka lower Riemann sums. Sa upper Riemann sums, kinukuha nating function value, yung supremum over the ith subinterval. Sa lower Riemann sum naman, kinukuha natin as representative function value yung minimum over that subinterval. Now, what will happen, or can we replace the minimum and the supremum by an arbitrary choice of a function value over the interval? And we will see later na yes, we can do that as long as we know that the function is Riemann integrable. And generally, if we will just choose a random c sub I or a random value on the ith subinterval to give us the function value na ilalagay ko dun sa analog ng Riemann ng lower o kaya upper Riemann sum, pwede pa rin mag-work yung mga theorems natin kanina. In particular, I will call that sum Riemann sum. And note of the use of the article "a" here, because the Riemann sum is not unique. Hindi siya katulad ng upper at saka lower Riemann sum where the multiplier inside the summation is fixed. Sa lower, lagi nating ginagamit yung infimum. Sa upper, lagi nating kinoconsider yung supremum. Pero pag kumuha ko ng isang arbitrary c sub I on the ith subinterval and use its function value inside the summation, what I'll get is a Riemann sum. Kasi nga arbitrary yung pagkakapili natin ng c sub I. Okay? And if we will do so, then the Riemann sum, such a Riemann sum, or actually any Riemann sum, will be less than or equal to the lower Riemann sum, but, will be greater than or equal to the lower Riemann sum, but less than or equal to the upper Riemann sum. Kasi nga, yung f of c sabay natin na pinipili as a multiplier inside the sum ay laging mas malaki sa infimum pero mas maliit sa supremum or equal. Alright? So ito yung relationship nating makukuha dyan. And Darboux's theorem will tell us that this could be another criterion para sa integrability. Okay? So nung sinasabi ng Darboux's theorem, basta si f ay bounded, then itong tatlong statements na to ay equivalent. Okay? Now, ano yung tatlong statements? Si f ay integrable on the closed interval AB. Tapos, yung limit ng upper minus lower Riemann sum ay equal kay 0, where P sub n is the nth regular partition of AB. Tapos, yung pangatlo, yung limit ng Riemann sum ay nag-exist and it is independent of the choice of C sub I. And moreover, the integral is equal to the limit of the Riemann sum. Okay? Pero mapapansin nyo, kahit itong meron dito mga special cases na, or actually nakita na natin yung proof ng ilang parts ng Darboux's theorem. Okay? Now, ang approach natin para rito sa proof na to, dahil ito ay isang equivalent statements theorem. Okay? So supposedly, kailangan ko ipakita na A if and only if B if and only if C, tapos A if and only if C. Pero by using the transitive property ng conditional statements or hypothetical syllogism, so marami tayo, kaya nating ma-reduce ito into a fewer number of things to prove. Okay? In particular, ang approach natin ay ipakita na si A if and only if B, tapos si B ay if and only if C. And these two guys, by hypothetical syllogism, will be able to conclude that A if and only if C. So, kompleto yung equivalent statements. Tapos, it is clear from the Archimedes Riemann Theorem na si A ay equivalent kay B. Okay? Kasi yung theorem 5.5, totoo siya sa kahit anong sequence of partition P sub n. Yung statement B kay Darboux's theorem, limited siya sa regular partition. Totoo nga yung 5.5 sa lahat ng klaseng partition. So, ano sabi ng 5.5? F is integrable if and only if there exists a sequence of partitions such that this is true. Okay? So, arbitrary yung pagkakapili ng partition doon kay theorem 5.5. Etong statement B ay specific sa mga nth regular partition. Okay? So that means carried over ito ng theorem 5.5, or it is actually a special case of theorem 5.5. So tapos na tayo dun sa kalahati. Tapos na yung A if and only if B. Yung sabihin nyo lang, it directly follows from theorem 5.5, yung Archimedes Riemann Theorem. Okay? Now, what we will need to focus on would be on B if and only if C. Okay? So yun yung gagawin natin dito. Now, let's start with a forward implication. Let's assume B. Kunwari yung limit ng upper minus lower Riemann sum ay equal kay 0, where P sub n is the nth regular partition. And we want to show that the Riemann integral exists, or the limit of the Riemann integral exists, and it is independent of choice of the C sub i's. Okay? So tingnan natin. All right? So ito yung assumption natin. Tapos from remark 5.4, yung kakasabi lang natin, this is true. The lower and the upper Riemann sum sandwich the Riemann sum. So totoo ito, independent of the choice of C sub i's. Kahit anong C sub i's, laging totoo ito. Tapos kukunin ko yung limit na magkabilang sides. Okay? Kunin ko yung limit nito, actually ng lahat ng sides. We know by assumption that the limit of the upper minus lower Riemann sum is equal to 0, and f is bounded, so therefore equal yung limit ng lower at saka yung limit ng upper. Para mag-hold yung limit nila ay equal, ay may difference na equal kay 0. So this and this have the same limit as n approaches infinity, so this theorem, the guy in the middle will also share the common limit. Pero ano ba ang limit ng lower Riemann sum? or limit ng upper Riemann sum, well, we know that that's going to be the Riemann integral. So therefore, the Riemann integral of f is also the limit of the Riemann sum. And since in this argument, we didn't use any mention about what the c sub I should look like, so we say that this limit will be true even if we have an arbitrary choice for the c sub i's. Okay. And then, hold on. All right, so that proves the first case, okay? Now, the second case, C implying A, ito yung medyo namumroblema pa ako dun sa proof. Ano? So, nakalimutan kong i-retrace ito. I was reading it last week, tapos nakalimutan ko na siyang balikan. Ngayon ko lang siya naalala na parang may problema itong proof na to. But maybe you can help me with this. Ang assumption kasi dito ay ang limit ng Riemann sum ay nag-exist and independent of C. What we want to show here is that the limit of upper minus lower ay equal kay 0. Yan yung gusto kong ipakita. Now, okay, kasama sa assumption na ito ay totoo. Alright? Now, ito yung problema ko. This is true for any choice of C sub i's, okay? So therefore, sabi rito ay for every n, choose C sub I such that this guy is true. That the function value of the C sub I must be equal to the supremum minus some small number, 1 over n times b minus a. My question actually here is, sure ba tayo na laging may nag-e-exist na C sub I? Okay. Sabi niya, piliin ko daw yung C sub I to be this guy. Pipiliin ko si C sub I to be the function, the element of the domain whose function value is equal to m sub I minus 1 over n times b minus a. Ang tanong na naglalaro sa isip ko last week ay, sure ba ako na laging merong C sub I na totoo ito? What do you think? Ito yung iniisip ko last week. Nakalimutan ko siyang balikan for today's video. So, may nag-e-exist nga ba? Alam ba natin na si little f ay continuous? No, we don't know that f is continuous. All we know is that little f is bounded. So alam ko nag-e-exist yung mi. That's a given. Now, why is it always that I can find a little c, okay, a little c sub I, such that the function value at that number ay equal to this guy? Hindi ko nga alam na si f ay continuous. Kasi kung siya ay continuous, pwede kong gamitin yung intermediate value theorem. Pero hindi siya continuous, ano? Kasi siya ay integrable, posible siya magkaroon ng isang ng mga points of discontinuity of measure 0. So, or kaya ko ba itong magawang less than? Siguro pwede ko itong gawing less than. Kaya ba yun? Pwede ko siyang gawing less than kasi alam ko si capital M sabay siya yung supremum. So, lagi ako unless this is a constant function. Kaya lang, hold on guys. Kukunin ko kasi yung sum. Gusto ko siya ay mas maliit kasi gagamitin ko siya dito. Kaya siya nagkaroon ng ganyan. Inisip ko ay palitan to ng less than. Okay. Papalitan ko yun ng less than or equal to. Yeah, madaling isipin na may nag-exist na C sabay na ang function value ay mas maliit ng konti dito sa supremum. Okay? Pero ang problema ko ay paano kapag si f ay constant function. Kasi pag si f ay constant function, then walang mag-exist na ganong function value. Kasi ang m sabay siya lang yung posibleng function value. So, Yeah. Kailangan kong isulat ng ibang direction yung proof. Magdadagdag lang ako ng isang case dito. Let's say case 1, f is a constant function. If that is true, then okay na. Mag-follow na yung proof. Kasi kapag kasi f ay constant function, yung lower Riemann sum ay equal sa upper Riemann sum ay equal din sa kahit anong Riemann sum. So mag-hold yung theorem. Pero kapag siya ay hindi constant, so ibig sabihin meron ka maximum at saka minimum value, magkakaiba yung function values nila. So, totoo na ba yun? Magkakaproblema pa rin ako dito pag masyadong malaki ito. Huwag siya dapat lalampas ng lower bound. So, pwede ko itong dugsungan ng ganito. Tapos mag-follow na, I think, this one. Tapos mag-squeeze theorem na lang ako para makuha itong inequality na to. Yeah, I think that should work. Sige, gagamitin ko yung pinagbabawal na technique. So probably your homework number 7 would be to write a proof noong C implying A. Ano? So you can follow this sketch that I wrote for the proof. Ano? Or if you can devise your own proof. Or baka naman makita nyo yung dahilan kung bakit sure tayo na may nag-exist na C sabay such that f of C sabay ay equal dito. Yun lang yung hindi ko maisip pa. Hindi ko pa sure kung bakit may nag-exist na C sabay such that the function value ay magiging equal to this guy. Unless alam nyo na, pero hindi kayo nag-share. So, yun na lang yung susunod na homework. Sumulat ng rigorous proof para dun sa C implying A na ito. Okay? Kaya na ba? Ang naisip ko kasing proof yung in-sketch ko kanina. Dalawang cases. Case 1 si f ay constant function, then everything will be well. Ano? Kasi yung upper saka lower Riemann, yung lower, upper, at saka yung Riemann sum ay magiging equal sa isa't isa. Kasi si f ay constant. So there would be no problem. Kapag si f ay non-constant, okay, pwede kong pilihan si C sabay to be this guy, to be the element of the domain whose function value is between the minimum and this guy. M sabay minus 1 over n b minus a, but I need to make sure that this guy will not be less than the minimum. Okay, so yun yung kulang dun sa argument. And then everything will follow. Pero I'll just leave the heavy lifting to you guys. So assignment nyo, homework number 7 will be to prove C implying A. Okay, tanggalin nyo yung butas na nakita ko dun sa proof na nasa lecture notes. Ano? Malas kasi nakalimutan ko siyang pag-isipan. So, sa inyo napunta yung trabaho. Ano? But I think that would be a nice exercise. Alright? Okay lang ba yon? Siyempre, hindi naman kayo makapag-object, no? So, yun. Kasi nakalimutan ko siyang pag-isipan. So, yun yung pinagbabawal na technique ng mga teachers. Ano? Pag ayaw namin isulat yung proof of pag-isipan, guys, assignment na lang ito. And lucky for me, kailangan ko pa mag-isip ng dalawang homework. So, ito na yung isang homework. Second to the last homework. Okay, and with that assuming to be settled, let's go to the next things here. Merong remark na nasusulat, which is basically a consequence of Darboux's theorem. Yung Riemann integral ay equal, nakita na natin dun sa Archimedes Riemann Theorem, ay equal dun sa limit ng upper at saka limit ng lower Riemann sums. By Darboux's theorem, we can add another equivalent value to it, and that is the the limit of the Riemann sum. Okay? So silang tatlo, yung limit ng tatlo na yan can give us the definite integral of f, or the Riemann integral of f over the interval AB. Okay? Tapos, itong konsepto na to, this can give us a nice way on how to find the limit of complicated sequences. Specifically, sequences siya ng mga partial sums. So for instance, look at example 5.11. Meron daw sequence ng itsura ng mga terms ay ito. 1 over n plus 1 over n plus 1 plus 1 over n plus 2 and so on. So sequence siya ng mga sums. Ano? So ibig sabihin yung A1 ay equal lamang kay, saan equal si A1? Si A1 ay equal lamang kay 1 plus 1 half. So that's going to be 3 halves. Tapos si A2 ay equal kay 1 half plus 1/3 plus 1/4. Si A3 ay equal kay 1/3 plus 1/4 plus 1/5 plus 1/6 and so on. Okay? So medyo komplikado yung itsura ng sequence, ano? Kasi bawat isang term dun sa sequence ay mga sums. So kailangan yung evaluate. Now, we can take advantage of the Riemann sum in order to find ano yung limit ng A sub n. Saan nagko-converge yung mga A sub n's? Kailangan lang nating isulat bawat term ni A sub n as a Riemann sum. Okay? So paano natin yung gagawin for this specific example? Yung A sub n ay summation lamang ng, actually kulang, sobra to. An I minus 1. Okay. This should be A sub n plus 1. Okay. Ito formula para kay A sub n plus 1. Hanggang A sub hold on. May mali na naman. Let's see. A sub n. Dapat ito ay okay, tanggalin natin to. Tanggalin natin yung A sub n dun sa problem. Ano? So, si A1 ay 1 half. Si A2 ay 1/3 plus 1/4. Si A3 ay 1/4 plus 1/5 plus 1/6. Ito kasi yung madaling paraan para mas kukunti na yung i-adjust ko. Ano? So, yung summation start na lang natin kay 1 over n plus 1. Para totoo na tong formula na to. Si A sub n ay equal sa sum ng 1 over n plus I starting from 1 until n. So yung summation, nag-start siya kay 1 over n plus 1, tapos matatapos siya kay 1 over n plus n, which is 1 over 2n. Okay? So ang idea, para magamit ko yung Riemann sum, kailangan ko itong isulat as a Riemann sum. Tapos saka ako siya kukunan ng limit. Okay? Kailangan sa Riemann sum, dapat equally spaced. Meron kang regular partition. So magpa-factor out ako ng 1 over n. Itong 1 over n na to, ito yung delta x sub I na gagamitin ko. Kaya yun yung laging first step. Mag-isolate ka ng 1 over n. Tapos, yung matitira, ito yung function f. Ito dapat yung f of c sub I natin. Alright? Then you can think of it as the function value of I over n. Siya yung itsurang 1 over n dyan. Okay? Siya yung pina-plug in. So what is our function f? Our function f would be 1 over x plus 1. Kasi dito natin pina-plug in yung I over n to get this. But again, our target is for this guy to be our f of c sub I. Okay? Kaya itong function, tapos itong pina-plug in, siya dapat yung maging c sub I natin. Alright? So that means I'm going to consider the function little f to be 1 over x plus 1 para yung f of I over n ay maging equal dito sa natitirang factor. Okay? So pag binuo natin yung Riemann sum with respect to the regular partition P sub n, okay, ito yung magiging itsura niya. Okay? Yung delta x sub I as promised would be I sub n. Tapos yung f of c sub I, siya naman ito. Tapos ang sabi, yung limit nito ay equal dun sa Riemann integral. But this guy is equal to a sub n, right? So when I take the limit of a sub n, I am taking the limit of this guy, which we know is the Riemann sum. Okay? So that means that's the Riemann sum. Pero alam natin yung Riemann sum, siya lamang yung integral ni 1 over x plus 1 from 0 to 1. Because our function little f here was known to be 1 over x plus 1. And then you can use the things that you learned from math 36 kung paano mag-evaluate ng integral, or 36 ba to or 37 na. So ang integral nito ay ln of 2. So that means the limit of a sub n, yung komplikadong sequence kanina, yon ay magko-converge lamang sa ln of 2. Oh, by the way, guys, when you're now integrating, you can use the theorems, the formulas that you learned from math 36, 37, and 38. Hindi nyo na kailangan kunin yung gumamit ng mga primitive concepts natin from the previous sections. Ano? So katulad nito, in-evaluate ko na lang yan as ln2 using the fundamental theorem kahit hindi pa natin siya napuprove. Pero alam na natin to from math 36. Or just to be fair, hindi ko naman kayo tatanungin about exact integrals, so you can leave it this way. Or kahit wala nga yung dx, kasi alam na natin na with respect to x ito. Okay? So you can say that the limit of a sub n as n approaches infinity is actually the definite the Riemann integral of 1 over x plus 1 over interval 0 to 1. Okay, so dyan nagko-converge yung an, which is a very complicated sequence, but thanks to these things that we have already learned, alam na natin kung saan siya mag-converge. Actually, magko-converge siya sa isang definite integral. Okay? Sige, isa pa. Ito naman. Ganun din, summation din siya, pero mas komplikado yung mga nandun sa loob nung summation para makuha yung nth term ng ating sequence A sub n. Pero nonetheless, kailangan lang natin itong isulat as a Riemann sum with delta x sub I to be 1 over n. Ano? So, tingnan ko yung formula para kay an. Tama na ba to? Yes, because yeah, kasi nagbabago lang naman dito, ay naka-plus dito. So this formula will be good because an here will be I starting from 1. So magkakaroon ako ng e to the power n plus 2. Yeah. And then kapag matatapos siya kapag si I ay n, so this would be so may problema na naman yata. Oh, tama pala. N plus 2n. There you go. N plus 2n. So that's fine. So ito yung formula ng an. Tapos kailangan ko lang siyang isulat as if it is a Riemann sum with respect to the regular to a regular partition. No? So what I'll do is to isolate 1 over n. Ito yung isolation ng 1 over n. Because again, later this will be our delta x sub I para sa Riemann sum. Okay? Tapos may constant, merong independent kay I. Ito, yung gumamit ng loss of exponents para ito masulat as this product. But this guy, nth root ng e to the n ay equal lamang kay e. So magkakaroon tayo ng 2 over e na constant. Pwede natin yung ilabas ng summation. That's how we got this. So natira na lamang that could serve as our function f would be 1 over e to the 2 times I over n, which is basically an expression for this guy. Tama ba? Okay, there we go. So here, this is our function f of ci, where our ci will be chosen to be 1 over n. Okay? Tapos, ibig sabihin, yung function f natin would be 1 over e to the 2x. Okay? So now, ganun natin siya masusulat sa Riemann sum. Okay? So, pag kinuha ko yung limit ng an, magiging limit siya nitong simplified expression na ito. Labas ko lang yung 2 over e dun sa labas ng limit. And then ito ay pwede kong i-treat sa Riemann sum. Riemann sum siya na ang function ay 1 over e to the 2x. Ang step size ay 1 over n kasi nga regular partition. Okay? So basically, this limit is the limit of the Riemann sum. And we know from Darboux's theorem that the limit of the Riemann sum is equal to the integral from 0 to 1 ng e to the power 2 to the x. Okay? And yeah, wag nyo na itong i-evaluate kasi kunwari hindi pa tayo, sige nga, hindi ko pa kasi nga pala na-prove yung fundamental theorem. Tapos pag ginamit niyo yung mga Math30 series tools nyo, fundamental theorem nga pala yung ginamit para doon. Ano yung antiderivative evaluated at the upper bound minus antiderivative evaluated at the lower bound. So medyo magiging circular yung reasoning ko. So kapag ka ganun, wag na lang nating evaluate yung integral. Ano? So now we know that the sequence A sum n's will converge to 2 over e times the integral of 1 over e to the 2x over the interval 0, 1. And no need to evaluate this guy. Mas madali yung para sa inyo. Hindi nyo na kailangan mag-evaluate. But we know that this guy is differentiable, is integrable because it is continuous everywhere. Dahil ito ay continuous everywhere, Riemann integrable siya everywhere per one of the criteria that we have established before. Okay? So, are there any questions about this? Sige, habang nag-isip kayo ng tanong, scroll down ko lang kung ano yung natitira. Okay. Any questions, guys? And then probably I'll end here. Tapusin natin ng maaga yung session today. Kasi kapag alanganin na, pwede kong start yung 5.3, pero hindi ko siya matatapos. And yung 5.4 naman ay super ikli. So I think I'll be able to finish 5.3 and 5.4 on Friday. Kung hindi man mag-extend tayo ng contest sa Tuesday next week. Ano? So, but yeah, I think this is a good place to stop. Tama ba? Mean value theorem lang naman yung mahaba ang proof. Mabilis lang yung proof ng fundamental theorem. Yeah, I think I can finish it on Thursday. So we'll stop here, unless you have questions. All right, no questions. Bigla akong magre-relax kasi ang dami pang oras pero kakaunti na lang. 7 pages na lang yung natitira sa module number 4. Okay, thank you, Trisha. So if you don't have any questions, so remember, I'll have homework number 7. Yung sinabi ko sa inyo kanina, C implying A. Kailangan lang natin ng C implying A ba yun o C implying B? Bakit ako C implying A ng C implying A doon? Kasi C implying A nakalagay. I think this is C implying B, C implying B. Bakit C implying A? Sinabi niya kasi it remains to show that B if and only if C. All right? So dapat i-prove natin yung B if and only if C. So pinrove yung B implying C. So ang gusto ko dapat i-prove ay C implying B. You know what? Riemann sum. So dapat yung lower. So yeah. Dapat C implying B ito. C implying B. Hindi C implying A. All right? So that's another typo. Okay. Bakit hindi ko to nakita last time? Last semester. Yeah. Ba't hindi ko siya na-correct last time? But anyway, so hindi ko matandaan kung anong ginawa ko last semester. But I think that would be fine. So you can follow the sketch that I have given you, or if you can think of why there really exists a C-sabay. Yun lang naman yung butas dito kaya hindi ko matanggap yung proof. Bakit sure tayo na may nag-exist na C-sabay such that the function value ay equal to this guy? Yun lang yung question mark sa akin. If you can explain why, then you can copy the proof and just insert bakit sure ka na merong C-sabay na totoo yung statement na yan. But I hope you see my question, ano? Yun yung malabo sa akin. So, kaya hindi ko matanggap itong proof na ito. All right? So I think we can stop there. 10 minutes early for a change. So let's meet on Thursday, hopefully to finish the course. But even if we finish it then, meron pa kayong ginagawa sa Math 155 for the next 2 weeks. Ano? So pero i-devote nyo na lang yung 1.5 hours natin per session para gawin yung mga natitirang homeworks o yung mga problem sets. Okay? So and then that I think wraps this meeting up. So thank you guys for bearing with me today. Medyo hindi ganun kaganda yung lecture kasi yung mga open questions ko ay ipinasa ko sa inyo, ano. So but I hope that's fine. At least we're thinking collectively and in a interactive way kahit hindi ko nababasa ko ng mga nasa isip nyo, but I hope you can read into my mind kung bakit ganun yung mga tanong ko about some of the statements here, right? So yeah, and then let's meet on Thursday again to finish the course. And until then, keep safe, guys. Bye-bye. Good luck sa mga natitirang ACADS.